Hey guys, welcome to the basics of momentum. We're going to learn a little bit about impulse problems and then some basic explosion problems in this video. And there should be another one about various kinds of collisions. So to begin with basics, in case you didn't know them or forgot them, momentum is represented by the letter P for reasons that escape me. Okay, so more or less momentum is P equals mv. That's what it is. There's a closely related term, though, which is impulse. Impulse is actually just the change in momentum. All right, so delta P is impulse. I don't know why. Again, why they needed a special word for it. Maybe it was just fewer syllables to say impulse than change in momentum. All right, so if if momentum is mv, impulse is m delta v, or alternatively, in a more complicated problem, since it's the integral of force, if that is a constant force, then impulse could also be represented by the equation force times time. And putting these two equations together is going to be a large part of how you are going to solve what are called impulse problems. All right, now later on when we talk about explosions, we will discuss the law of conservation of momentum. All right, like most conservation laws, what it more or less says is before and after are the same. All right, that's all that really conservation means, is it didn't change in between, right? It may be different looking than it was before, but the amount before and the amount after are identical. So when we talk about conservation of momentum, what we are saying is the initial and final momenta are equal. In impulse problems, that's not necessarily the case. In an impulse problem, the momentum of the system changes. All right, now what that really means is that it transferred the momentum to something outside of the system, okay? Momentum is actually always conserved, even when you do something like run into an immovable object like a tree. Okay, now, if you want to understand why that is, it's going to have to do with things like, well, the whole Earth is technically part of the system that you exist on. So if you take a step forwards, all right, you went from having no momentum to having some momentum, which means that since you're going this way, the Earth must have recoiled in the opposite direction. All right, obviously that's at least a little bit hard to fathom. Like, I moved the whole Earth? Well, yes, technically you did. That is actually what conservation of momentum says must have happened. All right, now, most of the time we won't consider the Earth as part of the system. And in those kinds of cases, you can talk about the change in the momentum of the system, such as for this car. All right, now, let's take the car crashing into a tree as a sort of classic impulse problem, right? You have an object in motion, its momentum changes due to a collision or the action of some outside force. Okay, and we want to know things like, all right, what is the force of the collision, or, you know, whatever, the time interval over which it happens, or something like that. Okay, so let's say that this car right here has a mass of 1,000 kilograms. And it's moving along at, how about 20 meters per second? All right, and the time that elapses between these two moments is, how about well, okay, I shouldn't say between these two moments. I mean between the moment when it begins to hit the tree and when it's done hitting the tree. All right, so we'll say that time interval is only 0.1 seconds. All right, so questions they could ask here. Part A might be find the impulse. Well, okay, impulse is going to be mass times change in velocity, okay? Or it might be force times time, depending on the information you were given, but in this case, it's going to be m delta v. So that looks like it would be 1,000 times, all right, final minus initial. The final velocity is obviously 0. The initial velocity was 20. And so that means that the change in momentum would be negative 20,000. Ooh, the units for it. Okay, units are two things. MV would give you units of kilogram meters per second. This equation, though, force times time, would give you units of Newton seconds. And so either set of units is acceptable. If you say kilogram meters per second or Newton seconds, that's the same thing, and either one's fine. All right, so let's say negative 20,000 Newton seconds, or kilogram meters per second. And that would be the impulse. All right, the next question might be, what is the force of the collision? All right, now this is, I have to preface, a little bit bogus. Usually during a collision, you don't just have one single force, okay? Usually the force during a collision would look something like this. All right, if I have a graph of force versus time, it would be like, hasn't hit the tree yet, hasn't hit the tree, oh, huge spike, and then comes back down. Okay, there we go. So this is when the collision is beginning. There's some maximum force that you reach that's sustained for a very short amount of time, and then force starts to drop off after that. Most collisions actually are going to look something like that, okay? All right, but be that as it may, we'll calculate here the average force using these two equations put together. If I say m delta v equals ft, the impulse I already calculated was negative 20,000. All right, and then the time interval is only 0.1 seconds, so that means that the average force is 200,000 newtons. Gadzooks. All right, well, that is a lot of newtons. If you're wondering, could anyone live through that? That's not actually the force that's applied to the driver. That's the force that's applied to the car, okay? If you wanted to look at the driver, then you'd be talking about his mass, his change in velocity, okay, which would be negative 20. The force applied to the driver is still very large, but nowhere near as large as the force applied to the car, since the car has a much larger mass. All right, so that's one example of an impulse problem. Almost all of them are going to be some variation on this. The only twist they can really add to it is if you have something where it doesn't, let's just say, come to rest, but say bounces off. So if you had something like a ball hits a wall and hits the wall going at 6 meters per second and bounces off going at 2 meters per second. All right, well, if you wanted to find the impulse or whatever, you'd have to do, m delta v, presumably. A lot of people will look at this and say the change in the velocity is 4. Oh, it's not 4. It's 8. It's 8 because if this is, let's say, positive 6 for the velocity, which includes the direction, that means this must be negative 2 because it bounced off of the wall and it's going the opposite direction now. All right, let's take a look now at some explosion problems. Explosion problems, or collisions for that matter, are all going to operate on the principle of conservation of momentum, which means that the initial momentum of the system, mind you, not of the individual objects, but of the system, is equal to the final momentum. Most of the time there's going to be two objects involved in a collision or explosion. So you'll have m1v1 plus m2v2 equals m1v1 final plus m2v2 final. This is like the one equation that you need for every conservation of momentum problem. Whether it's an explosion or a collision, it's going to use that equation as long as we're claiming that momentum is conserved during whatever the process happens to be. All right, so I'm going to start with an explosion here, and the next video will continue with collisions because they look a little differently. All right, so here's our scenario. Let's say Timmy, or whoever, is a small child with a mass of, how about 15 kilograms? Okay, he is standing on top of a wagon, which has a mass of, let's say, how about 25 kilograms? I'm probably going to regret choosing these numbers later, but that's all right. All right, so 15 kilograms, 25 kilograms. He sees before him a leaf pile. Timmy lunges towards the leaf pile, launching himself with a velocity of, let's say, 5 meters per second. All right, and then we want to know how fast is the wagon going to be moving in the opposite direction. All right, so assuming that they all start off stationary, using this equation here, I would get nothing but 0 on the left side. On the right side, I would have, all right, M1, if I take that to be Timmy, if he lunged at a solid 5 meters per second, which is an impressive leap, then we have the wagon rolls backwards with a velocity of, all right, well, this is some straightforward algebra here. We're going to get that V2 final turns out to be a nice and easy 3 meters per second. Oh, no, it isn't. It's -3 meters per second. Mr. Errico, does that negative sign actually matter? Yes, the negative sign actually matters. It actually matters a lot. It's one of the big things in momentum that people tend to mess up is signs. When things are moving in a particular direction, you have to have the correct signs for those things. So I would actually take off a point here if you did not put that negative sign in. All right, now it's going to be even more important when you're doing something like setting up a problem where things are already in motion, which we'll do in a minute. All right, now, before we carry on with that, I want to look at what would be the work done by Timmy. Work, Mr. Errico. We're doing momentum. I didn't know we're doing energy still. There's going to be a lot of energy wrapped into the momentum unit, so you have to know how energy works still. In a case like this, the work done by Timmy is going to be the change in the kinetic energy of the system. You can't get there using work equals force times distance, because I don't know anything about force. I don't know anything about the distance over which he pushed, really. But I can get the work by saying that it's the change in the kinetic energy. All right, it would work the same way if you had a question with like 2 carts right next to each other with a loaded spring in between them. The potential energy stored in that spring would equal the sum of the final kinetic energies of the carts. All right, now if you're looking at this and you're like, oh, well, I think they're going to have equal kinetic energies, you would be incorrect. It never works that way. Usually during an explosion, the smaller object has more kinetic energy. And that will actually definitely be the case here. All right, so pause the video, go ahead and calculate the work done by Timmy, and then resume it and see if you get the same answer as me. Timmy did 300 joules of work. Good job, Timmy. All right, now, if you got a different number, you can look over my calculation. You will notice I put a plus sign there. I did not subtract because the wagon's going the opposite direction. Energy is a scalar. They always add. Okay, so when we're figuring out like the change in kinetic energy or something for a problem, it's got to be the total kinetic energy for whatever moment you're looking at. All right, now we're going to run this problem now again a little bit differently. So the idea for this part is going to be, what if the wagon was already moving forwards at 3 meters per second? And let's say Timmy jumps off at still, well, let's say he manages to bump it up to 6 meters per second. All right, I want you to recalculate everything and then resume the video and see if you get the same answers I do. Okay, and there it is. The wagon actually does not change directions, is the meaning of that part. And the more complicated bit, the The work is the change in the energy. That's final minus